Hello, and welcome to the next video in the packaging series. My name is William Mitchell. Today, we're going to cover the basics of silicon photonics and then explore how the global semiconductor industry supports the new technology through cooperation and networking. The material in this video is brought to you by the University of Florida's SCAN Lab under the supervision of Litan Kumar Biswas, Shengji Ji, and Dr. Naveed Asadi. The first portion of this video will focus on silicon photonics as a technology, covering the basic principles of photonics, the advantages of working with silicon, and how silicon on insulator wafers enable photonic devices by making processing more accessible. We'll continue with major photonics components to explore the capabilities and limitations of photonic devices, then see how open access projects allow designers to collaborate with manufacturers. After we've developed a better understanding of silicon photonics, we'll explore how the global industry operates to support the relatively young technology and drive its development. By learning about the major players, designers, and manufacturers, we can understand the technology with a broad perspective. This will help us determine key points in the supply chain that are vulnerable to security attacks. Photonics is analogous to electronics. Both generate, detect, and manipulate a medium to communicate data in the form of bits. But unlike traditional electronics that rely on electrons to achieve this, photonic devices use photons, or light waves, to communicate data. Now, electrons have some significant innate limitations, one being that conducting electrons generate lots of heat as they move through a device, and that heat must be managed or else it can affect device performance or accelerate wear. Another limitation is that electrons have a finite mobility that depends on the properties of the conducting medium. This mobility will always be less than the ideal speed limit of the universe, light, unless you're working with a superconductor. And given the conductive medium is transparent, a photon can move at the speed of light unrestricted. So we've been able to harness the speed of photons to transmit large volumes of data across vast distances very quickly. And we do this every day with optical fibers, which dominate the communication landscape and allow you to stream this video right now. It's also a reason why photonic devices using optical fibers on the microscale have the potential to outperform traditional electronics in applications that heavily rely on the rapid transfer of data. Photonic devices are the result of using modern CMOS tools to fabricate tiny structures capable of communicating with photons. They rely on the same core principle as fiber optic cables to totally internally reflect photon beams and keep them confined within a structure called a waveguide. Now, the principle is defined by Snells Law and is related to the behavior of photons when they encounter a change in the refractive index of a propagation medium. Fiber optic cables will have a core that the light travels through that typically has a very high index of refraction. The cladding will have a comparatively low index of refraction and has the purpose of bouncing photons along the waveguide axis. Now, on the sine inverse function, a fraction with a lower value here will result in a smaller critical angle. The critical angle determines the minimum angle of reflection for a photon to totally reflect. Anything greater than that angle will reflect. If we make clever material choices to minimize the critical angle, these photons that would normally only partially reflect could totally internally reflect and remain within the core of the waveguide. Now, ideally, we want all photons to totally internally reflect. So by minimizing the critical incident angle, a photon interacting with the cladding will have more incident angle modes that achieve total internal reflection. Using high index contrast material systems, total internal reflection of injected photons can be easily achieved. Now, a clever choice of materials optimizes the transparency of the core and contrast of indices of refraction at a specific wavelength. And with that, the fabrication of photonic devices becomes achievable. Luckily enough, the material that has been studied by the nanoelectronics industry for decades, silicon, appears to be the best candidate for photonic devices. Now, pure silicon appears highly transparent to photons with a wavelength between 1200 and 3500 nanometers, making it a great choice for the core of our nanoscale version of fiber optic cables. At a wavelength of 1550 nanometers, the refractive indices of silicon and silicon dioxide are about 3.5 and 1.6 respectively, providing a nice contrast to promote total internal reflection. Since silicon has the ideal properties for a photonic device, we can take advantage of the massive scale CMOS manufacturing infrastructure that already exists to easily fabricate a slightly different kind of device. The CMOS industry has a history of exponential growth and has achieved impressive feats of engineering, fabricating billions of transistors on a single wafer. This means that the tools to fabricate photonic devices already exist, and they've been repeatedly improved so they have incredible precision and accuracy. The existing infrastructure in research and development is primarily where most photonic devices are being fabricated and their limits tested. Using the silicon on insulator wafer, silicon photonics is very friendly to existing fabs given the material compatibility. And since photonic devices have not yet made their way into many commercial applications or markets, research and development is the best place to test out new designs and develop a functioning, marketable product. The optical properties of silicon and silicon dioxide gives rise to a specific class of photonic devices being silicon photonic devices. The reason silicon photonics is so distinct compared to other material systems that may be able to create photonic devices is because silicon photonics can leverage the existing silicon manufacturing infrastructure, as mentioned before. Using photons, silicon photonic devices can achieve higher bandwidths while consuming less power and are easier to manufacture. While it has been an idea to fabricate CMOS alongside photonics on a monolithic chip, it's generally impractical and creates a lot more problems than it does solutions. A much better solution, which relies on having a common silicon substrate, is to apply the concepts of advanced packaging to integrate the functionality of photonics with electronics. The potential applications for silicon photonics build upon the existing applications for electronics, but specifically target high-performance computing and data centers. Other fields such as sensor, aerospace, and medical applications can also benefit from the technology as it becomes more established. Given the increased interest in advanced packaging over the years, a common silicon substrate that supports packaging with electronics is a huge advantage. The most common substrate used for silicon photonics is the silicon on insulator wafer, or SOI wafer. The SOI wafer is a wafer structure where a layer of single crystal silicon is separated from the bulk silicon by some sort of insulator, which is almost always silicon dioxide. The thicknesses of the silicon film and insulator layer can vary from 10 nanometers to 10 micrometers, while the thickness of the overall wafer may be in the range of a few hundred micrometers. Now, the smart cut process is a common process used to create silicon on insulator wafers and allows layer thicknesses to be carefully controlled. It starts with a regular high purity silicon wafer, which goes through a surface oxidation process that controls the thickness of the insulator layer. Hydrogen atoms are then implanted beneath the oxide layer to a depth that roughly determines the thickness of the top silicon film. This wafer is then flipped over and bonded to another new silicon wafer. The implanted hydrogen will create bubbles, allowing the wafer to cleave, and then using mechanical polishing, the surface of the wafer can be made ultra flat again. The final SOI wafer can then be cut from the handle wafer and then annealed. And using E-beam lithography, the patterns of waveguides and other photonic components can be easily transferred to the SOI wafer by etching through the silicon film. The isolated silicon that is left will be the core for our waveguides. Then, additional silicon dioxide can be deposited on the wafer to encapsulate the silicon cores with the silicon dioxide cladding to effectively form optical waveguides on the microscale. Now that we have silicon on insulator wafers to help us fabricate our silicon photonic devices, we can talk about more complex and well-known components like lasers, modulators, and photodetectors, in addition to the simple waveguide. Similar to how electronic devices need a source of electrons to function, photonic devices need a source of photons to function. And in order to do this, photonic devices need lasers to generate photons at a specific wavelength. Now, typically, lasers are fabricated using 3,5 compound semiconductors, such as gallium arsenide, as they have superior optical properties when it comes to efficiently generating and emitting photons. 3.5 lasers induce some material challenges though, such as requiring very high processing temperatures and generally being hard to grow on silicon due to lattice mismatch. They are essential to the function of photonic devices though, and allow electronic signals to be converted into optical signals. Now, waveguides are seen on photonic devices routing photons around and are primarily designed to ensure total internal reflection of photons generated by lasers. Waveguides have a lot of capabilities, often being used to bend, guide, and split photons as well as simply guide them. Couplers do more complex operations on photons and control the phase and optical modes of photons to inject and extract them to and from waveguides. A common type of coupler is called a grating coupler, which allows photons from a fiber optic cable to inject into the waveguides on an SOI wafer. Couplers in general also have the ability to split, combine, and route photons within a photonic device. Continuing on with major components, we have transmitters and receivers. Now, transmitters are essentially lasers or photogenerators that have the ability to convert electronic signals to optical signals. Receivers are the opposite. They are photodetectors that have a very similar structure but convert optical signals back to electronic signals. Now, transceivers are components that have the ability to both transmit photons as well as receive them. Transducers are components that use electronics, magnetics, or acoustics to modulate light waves. And the purpose of modulating these light waves is to encode and control or correctively tune photons by altering their measurable properties such as amplitude, phase, frequency, and polarization. The main goal of transducers are to bridge the gap between electronics and photonics, allowing the data carried by photonic devices to later be processed by CMOS logic. Designs for photonic components, such as those we just talked about, have been compiled into libraries called process design kits. These libraries allow end users like device designers to submit designs and receive process chips, fostering innovation in the field of photonic devices. Components like waveguides, modulators, transmitters, and receivers are all represented as building blocks for designers to mix and match and create unique photonic devices. Foundries will protect their intellectual property by simplifying components and withholding the process flow, but do provide technical and dimensional details to aid design. Now, the figure here is an example of a photonic PDK. We can see the phase modulator is represented clearly, and we can see what's actually going on. Someone who's more educated in the field of photonic device design could use these building blocks in a much more complex circuit, such as the one on the far right here, for any sort of application, and the open access nature of process design kits enable that. Designers can also design their own building blocks to go into these PDKs that follow the design and fabrication rules of the foundry to better push the limits of these devices. Some limitations that are set by the foundries may be the minimum isolation between components, the maximum wafer depths, or the maximum feature sizes. To optimize silicon photonic fabrication, foundries offer two options to maximize efficiency depending on the designer's goals. The first option is called multi-project wafer mode, where various different chip designs or projects are fabricated together on the same wafer. This option is best for research and design applications because it allows multiple end users that are submitting designs to share the tooling costs, mask space, and wafer resources. Devices that are preliminary or in very low demand may choose this option to save on cost. The alternate option is to use the full reticle of the wafer to fabricate a single photonic device in higher volume. It may increase the initial cost since you're fully responsible for the tooling and resources, but it reduces the overall cost per wafer in the end. Well-tested devices that have high market demand may choose to use the full reticle for high volume manufacturing and device consistency. And though we're talking about photonic devices, the major measurables of device fabrication remain unchanged. Foundries are always looking for a high process yield, high density of devices per chip, and all to maximize performance. Performance is maximized by maximizing the speed and minimizing the consumed power, device footprint, and manufacturing cost per chip. The global semiconductor industry includes a diverse set of companies from across the globe, many of which have shown increasing interest in silicon photonics. Some are old electronics companies or established research institutions, and others are newer players that primarily focus on developing photonic devices. And the global market for the technology is predicted to nearly quadruple from the year 2023 to 2030, and has gained a significant amount of attention over the past decade from major players in the electronic industry like IBM and Intel. These companies, or major players, have a lot of capital and a lot of infrastructure, giving them complete control over the design, manufacturing, and integration of devices. Essentially, these major players leverage their dominant presence in the electronics industry and can afford to invest a large sum of money into research and development. Intel is widely known as a pioneer in the silicon photonics industry, as they are already a semiconductor powerhouse. They have plenty of resources to develop and manufacture their own silicon photonic devices completely in-house. IBM is another company of similar stature, often on the forefront of the technology and known to integrate silicon photonics into their data center solutions. Broadcom and Cisco are also big names to see in the data center, networking, and telecommunications applications fields. They're looking to expand into silicon photonics as a way to enhance the capabilities of their existing products and services. Also mentioned here is NVIDIA, who are venturing into silicon photonics to support high-performance computing and AI workloads by integrating with their GPUs and AI architectures. Now, these aren't the only major players in the industry, but just a small selection of big companies with big name recognition. None of these companies are primarily focusing on silicon photonics, but they do have a significant impact on the technology by driving it forward using their access to resources. The primary minds driving the innovation of silicon photonics are classified as design houses in industry and research institutions in academia. These entities are dedicated to commercializing existing silicon photonics devices and designing new photonics components with enhanced performance. OpenLight is an example of a design house that focuses on providing accessible photonic integration platforms, accelerating development of photonics applications. Lightelligence and Lightmatter also specialize in developing silicon photonics-based solutions for high-performance computing, aiming to revolutionize how data is processed and transmitted. Ayar Labs pioneers optical input-output technology, focusing on overcoming the bandwidth limitations of traditional electronic interconnects. Universities like UCSB, Columbia, Stanford, and MIT often collaborate with industry partners as well as each other to explore novel materials, architectures, and integration methods. CEA-Leti is a French research institute which also has made significant contributions to the development of microelectronics and photonics. All of these institutions work in collaboration with Foundries to accelerate the viability of silicon photonics in modern-day computing applications. The companies who solely manufacture and assemble electronics possess most of the crucial silicon manufacturing infrastructure required to enable the fabrication of silicon photonics. Major foundries like TSMC and Global Foundries have expanded their product lines, also investing in silicon photonics. Other foundries like Tower Semiconductor, IMEC, and ST Microelectronics are much more invested in silicon photonics, as they provide customizable foundry services in the form of PDKs for design houses that are prototyping photonic integrated circuits. These well-established fabs help increase the manufacturing efficiency of existing silicon photonic devices and reduce the cost for rapid prototyping, ultimately accelerating the adoption of silicon photonics. Packaging and testing facilities like Fix, Jabil, VLC, and Ficontech help integrate silicon photonics with existing electronics through advanced packaging methods. They also support the commercial development of the technology by designing devices that combine the principles of electronics and photonics. The collaborative nature of the various players in the silicon photonics ecosystem is extremely important for the development of the technology. Large-scale fabs like TSMC have decided to closely partner with other designers or researchers to gain an edge in the market. TSMC decided to partner with Ansys, an industry-leading company that focuses on simulation solutions to aid the co-packaging of photonics and electronics for high-performance computing. Ansys gets to primarily focus on innovating the devices, while TSMC primarily focuses on efficiently manufacturing the devices. The relationship works very well and makes prototyping very easy, encouraging innovation. Now, a similar relationship can be seen between STMicro and Luxtera. STMicro provides the reliable, scalable, and cost-effective supply chain for the silicon photonic designs produced by Luxtera. These symbiotic relationships between industry partners allow specialized companies to share resources with a common goal of innovating silicon photonics. Since these companies don't have the industry presence to do everything themselves, partnering up gives them much more control over the supply chain. Now that we understand how the silicon photonics industry is a complex, global networking of numerous companies, we can take a look at where security vulnerabilities may be an issue. Now, it's not uncommon for a system designer to have their products manufactured in a fab located in another country. In fact, a single design may be sent to multiple different foundries to fabricate all of the necessary components, like other discrete devices, interposers, co-packaged CMOS devices, and of course, the silicon photonic device itself. In this step, there are a lot of moving parts and potential for unwarranted modifications that can lead to denial of service attacks, data leakage, and reliability and integrity issues. After all of these components are fabricated, they then need to be assembled and packaged, which gives rise to more security vulnerabilities as the device is sent across the globe before it finally reaches the end users. As a relatively new technology, the intellectual property surrounding silicon photonics is extremely valuable and also vulnerable to attacks like this, just like electronic devices are. Because of this, it is incredibly important that we continue to develop security assurance measures to mitigate the evolving threats of the modern computing age. To wrap it all up, photonics are not going to overtake electronics as the primary computing method. Instead, the goal of silicon photonics is to seamlessly integrate with existing electronics in order to enhance their functionality. Now, the main reason for this is the fact that photonic components must be large enough to contain the wavelengths that they carry, which is typically 1 to 2 microns. In contrast, the electronics industry has been able to achieve transistors the size of just a few nanometers, which allows for an unmatchable computing density. While photonics may be able to travel at the speed of light, they are not too good when it comes to dense computing structures, and for this reason, many companies are turning towards packaging solutions that pair photonics with traditional chiplets to experience the benefits of both. The purpose of photonics in co-packaged devices is leaning towards data communication, focusing on the transfer of data rather than the actual computing of logic. Optical connections can pair dedicated logic dies with high bandwidth memory stacks in order to increase transfer speeds and compensate for the weaknesses of electronics. Many of these designs are still prototypes without much market value, but they are innovating on silicon photonics with hopes to bring the technology of the future to the present and revolutionize how we communicate data. As with most leading-edge technologies, silicon photonics still needs more time and refinement in R&D to fully live up to its promises as a next-generation technology. While there are challenges ahead, the integration of photonics and electronics offers exciting opportunities for advancing data communication technologies. With continued innovation and development, we can look forward to a future where these technologies work together to create more powerful and efficient systems. If you would like to explore further on the topics discussed in this video, the sources listed in the bottom left of each slide are referenced here.